be here to talk to you among this women pioneer robotics. So I'm from Stevens Institute of Technology, and maybe not everybody know where it is. So we are in New Jersey, the cross river from Manhattan. So that's our campus, and I don't have the pointer, but we overlook the lower Manhattan, and that was on the top, that was the old World Trade Center site. So we have like, we're engineering school, we're a small private university with about 5,000 students. And the School of Engineering and Science is the biggest school. I direct the Robotics and Automation laboratory in Department of Electrical and Computer Engineering, and we have the common use research robotics platform, including the pioneer robots, turtle boats, and of ocean engineering, they have the Department of Homeland Security, Center of Excellence. There are a bunch of people doing some robotics related work for ocean applications, and at the bottom of the picture, that's the tow tank and some underwater vehicles. I collaborate with them in that project. Okay, so today I'm going to share with you some of our recent results using marine robots to monitor the ocean pollution Plume. And I'm going to first introduce the motivation and formulate the problem, and introduce our algorithm. I'll show the simulation MATLAB, which is basically validate the algorithm, and then we show the we did the simulation in robot simulator. All right. So I don't think I need to say much about the potential damage of the recent deep water oil spill. So it's difficult to estimate to what extent the damage is. So my collaborator, Dr. Graham Bingham from Newport, Hawaii, we got this NSI project to invest this problem. The picture on the bottom left, that's a sensor. If you put the sensor, chemical sensor on the robot, it can detect the oil slick values. So the point is, there in robotics community we have many smart algorithms, but in the field test there's a missing gap between the advanced algorithm and what they can really do in the real world problem, such as the marine engineering application. So we are fortunate to be funded by this project. It's a 30-year project, so we made some progress, and I'm going to talk about our progress. So the existing work on the underwater navigation, when we did the review, and existing method can be roughly categorized in 3 types of methods: mapping-based approach, behavior-based approach, and control-based approach, which is in the next page. The mapping-based approach, basically, they first use the robot to build a concentration map of the environment and then track the Plume. Obviously the whole area has to be surveyed by sensors, and we use a preview map to navigate. And the second behavior-based approach is combine certain elementary behaviors to track a Plume. The drawback is no guarantee of conversion. It works in many cases, but you know, on the contrary, the control-based methods considers robot dynamics. It have provable correct algorithm that can guarantee convergence, but almost all the existing work considers static Plume without the dynamics propagation. So we consider the dynamic propagation of the Plume from, and we use the multi-robot to track the dynamic Plume from. If we think about the chemical pollution, point source pollution in the ocean, the propagation has this physical model, oceanographic model, the so-called eventual diffusion equation I put there, which basically is a partial differential equation, and it's modeled the process that the Plume will go with water flow direction and also diffuse on the tangent direction of that. And our goal is to deploy multiple robots dynamically track the Plume from, right? And the Plume from travels slower than the speed of robots, so it's durable. And in multi-robot case, we don't want to use all communication. We want to impose this nearest neighbor communication in a sense. We have a leader agent and anchor agent with the person last, and all the other are follower agents. So it's only the neighbor-to-neighbor communication, save the communication cost. What we do, we study the dynamic Plume tracking problem, and the main contribution, as I said, we impose this dynamic algorithm, and we explicitly consider the eventual diffusion model of the Plume model. And our solution is an analytic solution without numerical solutions, so it's real-time implementation. Okay. So I'll talk about some details about algorithm now. First, how we formulate the problem, and we consider the robot model as a single integrator. You may say robots are not single integrator model. That's true. But for many robots, including the surface model, the unmanned surface vehicle, through a nonlinear coordinate transformation, they can be transferred to the single integrator model. And the Plume model, the second equation there is the advention equation, diffusion advention equation, which is the PDE. Solving PDE of their state time, numerically it costs computational resources. We avoid solving that, but we consider the source going with that. And V, that's flow constant, K is the diffusion constant. And the third bullet from Plume from definition, what we track is defined by this CXT equal to C0, which means that we consider a constant concentration value as a from, and this is time where it will move along the time, right? And we assume the robot can sense current position and the flow velocity. This are common and is durable. They have the sensor to sense the flow and the robot position. And we assume the robot can detect the chemical concentration CR at the robot place. For the gradient and the divergent gradient, which is the second derivative, we may estimate it. Although in this work, we didn't use the estimate value, but we could incorporate that in future work. So the problem for single robot tracking is to design control law to drive the robot to track and patrol the Plume from. So it catches the Plume from and will move along the tangent direction of the plume. And for multi-robot, not only tracking, we want the multi-robot to evenly distribute along the plume front, where I'll show more videos. Okay, so the challenges are, without solving this partial differential equation, how do you incorporate the model of the plume? For multi-robot, we want to do both plume front tracking and petrol with formation. We do that through estimator and control framework. I don't think I have time to talk about all the math, but basically the idea is we don't know where the front is, but we can, based on the robot measure concentration and robot trajectory, we can estimate where we build the observer to estimate where the plume front is, and then we design controller have robot track the plume front. So the general control diagram is on the right. Plume dynamics, we have measured CR, is a measure or estimated the gradient and divergence. Then it fits into the observer, which estimate where the plume front is. Then the x-axis is the estimated plume front. Then it input into the controller, and the controller goes into the controller robot to track it. So there's some math involved in it because it's a partial differential equation. It's definitely more harder than ODE model. So there's some simple minimized approximation and some mathematical operation on that. I'm skipping this. I deleted my students' slides of 5 pages also here. And for multi-robot, for the first and the last robot, it's the same controller as a single robot. And for the follower robot, it has a formation controller terms so that it can evenly distribute between the first and the last. The first and last one will go at opposite direction of the plume front, so they will meet. Okay, so this is a controller for the follower robot, UI, and okay, so I saw the chair stand up, so I may have only a few minutes left. So the simulation, I first show the MATLAB simulation. In order to do a simulation, you have to do the environment, simulate the environment. And this has 2 parts. One is a flow field that's simulate the current flow. We solve the so-called Navier-Stokes equation with boundary constraints. For the plume, here you see 2 sources, top and bottom. The red of theirs has high concentration. Then in this paper, the black arrow are the current direction. You can see it could be time varying. To get the concentration field is a numerical solution of a partial differential equation using the finite difference secretization in space and Euler forward expectation in time. So this is not part of the controller, but this is part of generating the simulated environment. Now I'm showing the MATLAB simulation. This is for one robot. Okay, one source S2 there, and the robot is a circle. So let me run it. So you can see the robot is the red circle. It goes with the front. I think this is like twice faster than the actual red. And for the multi-robot, initially they are together. These are 30. Whereas we cannot deploy 30, but we have these fours, and these are the multi-robot all together. And you can see the red one, the first and last one, and the other blue rectangle are the follower robot. They quickly distribute between the boundary robots. So we use that. The algorithm can rigorously prove the estimator controller converge. And the MATLAB simulation is to validate the theoretical statement. But obviously, in robotics, we got to do the experiments, and we simulate in a robot simulator, and this simulator is developed by our collaborator at University of Hawaii. They have this robotics lab vehicle software platform. It's very similar as WALS, use LCM, and it's a collection of hardware drivers, real-time control process. And on the top, a figure that's the simulation mode. And the bottom is the real-time control mode. It's easy transit to the field test. And the Plume model, one main important thing here is that you have a nice algorithm, but where it works, it depends on whether your model is really consistent to describe this real environment. So we have students studied half year for this Plume model, and incorporate some real world effect like wind or tide, other effect into the model. You can see on the picture here, this is a MATLAB simulation of the environment, which is ideal case, and then you can see some like particle kind of simulation which is noisy, that's more close to the real environment. Okay, the temporal concentration you can see is more noisy. So use this environment model. We implement the algorithm in the robot simulator using LCM, and I'm going to show the simulator simulation. You can see successfully the single robot green dots successfully control the room front. And for multi-robot, we didn't have 30 robots. We only simulate like 3 robots. They are together in this small picture, but actually they keep certain distance between them. The red one, if you can see it, maybe you cannot. Initially we thought we could do it in a controlled about the environmental requirements, but fortunately the UH have a very nice on-site, not on campus, but nearby site to field tests. They previously did the real robot test in a harbor environment for Coast Guard contracts. So they have a place to put the vehicle on the lab. The surface vehicle platform is what they built. And the picture I took last year when I visited there, it's a nice, you don't have very rough current. It's peaceful harbor environment. So we've been talking about the experiments and working towards field tests. So I conclude here that we consider the cooperative tracking of the dynamic ocean plume. We explicitly consider the plume propagation model, and we designed the estimator controller framework, and with the simulation MATLAB, and also in the robot simulator. Okay. Okay, so that's our collaborator, Dr. Bingham at UH, and on the right, the picture of the students with some of his group students visiting us in the summer. Okay, that's it. University of Hawaii. Dr. Bingham. Yeah, Bingham. Binham.
Yes. Very interesting work. Do you incorporate current models into your system? Water current?
Water current? No, that's a parameter V in the equation. We assume it's no, because the robot can be equipped on a current, the sensor that can sense the current at the robot position. We assume that parameter is no. But the V could be constant, could be type R, it's big T. Yes?
Thank you for sharing. I didn't get a good look at the control and estimation algorithms, but have you considered what happens if one of the followers of the nearest neighbor topology goes offline or drops out? Does it quickly reestablish with the next nearest? Or?
Yeah, the controller for the